During this session I'm going to be talking about electric current and resistance. So really I'm going to be considering what happens inside an electrical circuit with respect to the current and the motion of charge and stuff getting in the way of it. So first of all I want you to try and imagine. Imagine you could look inside a wire. What would it look like? What would be happening? What would be going on? Getting some of the ideas straight in the first place really helps understand, I guess, thinking microscopically helps us understand macroscopically what we can measure, what we can record. So I'm hoping if you're imagining inside a wire, what you're imagining is lots of electrons. These are my little black dots here, bobbling along, moving from one place to another. Not necessarily going in a straight line, occasionally bumping into the copper atoms. I have a copper wire in my imaginary wire here, and getting in the way, but generally the current and the charge is passing from one place to another. So this flow of electrons, what we call the flow of electrons, is the electrical current. It's the amount of, well, rather than the amount of electrons, it's the amount of charge which passes a certain point per second. So that's the electric current. And we can see the current flowing through this wire at this moment in time. Now, just a kind of a little note here, and aside to some extent, the flow of charge, so the flow of the electrons, and the direction of the current is often seen as a misconception that these two things are kind of opposite. So what happens is that the flow of electrons goes in one way, but the way that current is shown in the other direction. In reality, what happens is what current does is that the direction of current shown is shown as the direction for positive particles. Although the electrons are flowing and they're negatively charged, we do have positively charged particles as well, and current shows that. So, if you really want to get down to the nitty-gritty, I suppose, the direction of current shown on some diagrams would be in the opposite direction to the direction of the electrons flowing. An aside, but worth commenting on nevertheless. So let's think about this in a little bit more detail. The flow of charge, or the electric current, is measured in amount of charge per second. So charge is coulombs, and it has the symbol Q, and obviously time is measured in seconds. That gives me charge per second, gives me the current. And the unit for that is amps, and the letter which we use is the letter I. So we can also think about that charge equals current times time. Now just remember that the units always have to be in seconds, as always in any physics style calculations. So with that in mind, I'm going to give you a few questions now. So here's two questions. I'm going to allow you to press pause. And now you've completed those questions. Let's check to see if you've got your answers correct. 36 coulombs and 18,000 coulombs there. Another couple of questions. Okay, now you've completed those questions. The current is going to be 0.2 amps, and the charge that has passed by is 4,320 coulombs. Okay. So there's some calculations joining up time, charge, and current. The flow of charge, and I mentioned that flow of charge doesn't always just mean the flow of electrons. There are some other situations as well, so I just kind of mention these things. In molten ionic compounds, we can have negative and positive ions. In aqueous solutions, we can also have negative and positive ions, so that we can have negatively charged and positively charged ions as well. These all could build up and be involved in current. So it's the flow of charge, the change in location of charge. So I've spoken about the flowing. Another thing I want to think about is the things which cause it not to flow. This is the resistance. The things which resist the motion of electrons. Now, from the beginning, my statement says electricity in wires is a flow of electrons along the wire. As electrons move along the wire, they collide with the metal atoms. These collisions make the atoms vibrate more, which makes the metal hotter. So whenever there's a change in temperature, it means that those copper atoms are vibrating more and more and more, and this in turn will make it more difficult for those electrons to get by. So that's one issue. That kind of copper atoms getting in the way, or stuff getting in the way of electrons travelling, is known as resistance. So the resistance is a measure of how much material tries to stop electricity passing through. Okay. So I've already mentioned one feature here. Let's just think about our system. What other features will impact electrons travelling? Well, I've already mentioned temperature. So the more these vibrate, the more they get in the way of the electrons. We also think about the overall area of the wires. That means how wide it is. So how much space there is for electrons to be able to pass through. We can also think about the length. The longer this wire is means there's more atoms in the way, so it's going to cause more problems for electrons to pass through. Generally, there's also the material itself. Copper, although there's all these copper atoms in the way, has quite a good at allowing electricity to pass through, and that's described as the resistivity. And all these things build up into the resistance. So let's take us through that again. The factors that can impact resistance are the length, the area, the temperature, and also the material. Now, all these things combine. So resistance is equal to the resistivity, which is dependent on the material, times the length divided by the area. Resistance is resistivity, which is always given the symbol ρ, times length divided by the area. Notice the temperature isn't included in this calculation, and it's an issue that we often have to assume is going to be staying constant, or we have to recognise the impact of its change, and we'll think about that a little bit later on in the course. So, with that understanding of what impacts resistance, here's a question. What is the resistance of a 1 metre of copper wire with a cross-sectional area of 1.5 millimetres squared? Now, first of all, it's stated as copper wire. So to do this problem, what you'd have to do is you'd have to look up and find out what the resistivity of copper wire is. As it happens, it's 1.72 times 10 to the 8 ohm meters, which are the units. The length I know is 1 metre, so that's been given to us. And the area is 1.5 millimetres squared. So remember, thinking about this, milli is 10 to the minus 3. So 10 to the minus 3 squared gives me times 10 to the minus 6. So I've got 1.5 times 10 to the minus 6 metres squared. That's what I've been given. My unknown is resistance, and my equation is that as shown. I can then put in my values, and out comes a final value of 1.15 ohms. And that's how you can calculate the resistance, considering all of the issues involved in the factors which make that resistance. And that closes the idea of electric currents and things which resist electric currents, the things which stop that flow of electricity.